Welcome back. Now let's code the same sequence detector wherein we are looking for a symmetric sequence 101, but let's code it and let's capture it using the mealy machine. Fine. So again, I will start initial state. Let's call it as 0. This is my initial state. And now the outputs will be conditional because we are trying to capture it using an FSM. So in this state, S naught, I am looking for the first bit of my sequence, which is 1. If I don't get it, so something like this, if I get a 0, then my output will be 0. Fine, and I will stay in the same state. But if I do get it, if I detect a 1, then I will move to a next state S1. So this happens for X, and again my output is 0 because my output will be 1 as soon as all the 3 bits of the sequence are detected. Now in the state S1, I have detected 1. Now I am looking for 0. If I don't get a 0, if I get a 1, that means the first sequence is broken. It's not complete, but I have detected the first bit of the next sequence. Output still will be 0. And if I get a 0, let me introduce another state S2. So this transition happens when I have the 0. My output is still 0. Fine. Now from S2, I am looking for 1. Now this is very important here. This is very interesting. If I get 1 after S2, my first sequence is complete and my output will be 1. Simultaneously, the first bit of my next sequence is also detected. So it will be a transition something like this, wherein I am getting a 1, X is equal to 1, and my output is 1, and I am moving to sequence as a state S1, wherein the first bit is already detected and I am looking for the next bit. Now in S2, if I get a 0, which means my sequence is broken and I have to start from the scratch from the first state. So it will be a transition like this, X bar, conditional output 0. Then I will repeat the same process. So in the mealy machine, I'm actually saving one state. If you remember in the Moore machine, we had used 4 states, but there for a particular state, output was defined. This is a mealy machine. I am saving one state, but my outputs are conditional. So this is the first step. We have captured the state machine. So this is the first step wherein we capture the FSM. This is the mealy machine. Second step is we create the standard architecture. The thing here is, although I have saved one state, but I will still require 2 bits because to encode 3 states, I will need at least 2 bits. Let me see if I can move it. Right. So the standard architecture will be something like this. You have the resolved sequential part and the unresolved combinational path. So the resolved sequential is basically 2-bit state register with the clock. So you'll have 2 outputs from here. S1 as usual and S0. Fine. And then you will get your next states N0 from this side. Then N1 from here. Fine. So this is S1, S0. This is N0, N1. The combinational logic is to be resolved, but we will have X as one of the inputs and Z as the output. So this will be the standard architecture. Third step is we encode the state machine. Again, I will show it here only just to save some time. The 3 states, instead of using alphabetical names, we will code them. So let's use the code 00 for this, 01 for this, and 10 for this. Then we'll create the state table. So this is the fourth step, create the state table, wherein I will list the inputs, which is S1, S0, and the external input, and the outputs. Fine. So if I'm currently in state 00, and my input is 0, my output will be 0, and I will stay in the same state. Then 00, and my input is 1, still my output will be 0, but I will move to the state 01. Then in 01, if my input is 0, still my output will be 0, but I will move the next state 10. And in case my input is 1, output is still 0, and will continue to stay in the same state. Then in 10, if I detect as 0, output is still 0, and I will move to the initial state. And in 10, if I detect a 1, this is when my output will be 0, and I will move to the state 01. Because detecting the third one, the third bit, which is a 1 in the first sequence, also detects the first bit of the next sequence. That is in fact the catch here, that the sequence is symmetric. Sometimes it may happen that the sequence is not symmetric. So in that case, once you have detected the 3 bits, then you'll have to start from the first bit itself. Fine. Then you can resolve it. I think you can do it. So for Z, I will actually have a single term here, S1, S0, X. Again, you can use the don't care conditions if you wish. Fine, because again it has six valid combinations, two combinations, 110 and 111. They're not a part of this state table. So if you are using K-map, you can mark them as don't care, then combine them to form larger. Let's actually do it. I've been saying it for so much time, so let's do it in this case. So I have two inputs here, which I'm not considering as the state table. So one of the inputs is 110, 110, and 111. So I don't have any specific outputs here. Fine. So let's call a K-map. Let's call a K-map here. Let this be a 3-variable K-map. Fine, I need it for 3. So we'll do one thing, we'll first copy it. Yeah, let's first put out the variables. So I will have S1 complement, S0 complement, S1 complement, S0, S1, S0, S1, S0 complement, then X complement, X. So let me copy it 3 times. Fine. So let this one be for Z. Okay, just a second. For the output Z. And as you can see, this is min term 0, 1, 2, 3, 4, 5. Only for 5 it's high. So 0, 1, 2, 3, 4, 5. But I have don't cares here and here. In fact, for every K map, I will have these two as don't cares. Then you can exploit don't care here. So you can have a combination, something like this. Fine. And this will give you a term. This will give you a single variable term. Sorry, a 2-variable term that would be S1 X. Fine. Then let's move on to let this one be for N1. So I have 0, 1, 2, 3, 4, 5. Only 2 is here. 0, 1, 2, 3, 4, 5, 6, 7. Again, you can have a combination here. Something like this. Fine. And this will give you S0 X complement. Fine. Then likewise for N0. N0 I have M1 is there, 2, 3. So 0, 1, 2, 3. Then I think so 0, 1, 2, 3, 5 is also there. 4, 5. So okay, you are able to form a larger combination here like this, which means n0 will be actually x. And so these are very simple terms. You can easily implement it. So let's implement it here only. Let's get rid of this table. I no longer need it. So I will have the sequential part, which is already resolved. It is a 2-bit state register, of course, with a clock. From here, I have two inputs, S1, S0. Then I also have an external input. Fine. So this right here is S1, this one is S0, and the one in navy blue is X. Fine. And let's first implement the output Z. It is simply S1 combined with X using an AND operator. So that would be my Z. Then for N1, I have S0. Here is my S0 and complemented X. So that would be my N1. That will be fed back here. So this is N1. And N0 is directly X. So you can tape out a connection from here, feed it back. So this is N0. Fine. And this will be the circuit for this sequence detector using the concept of mealy machine. Fine. So similarly, you can have different problem sequence detectors, waveform generators are there. Yeah, you can change the sequence. You can have multiple, problem definitions in terms of these sequence detections. These are basically used for the design of controllers. Controllers and timing counters are a part of your timing circuits, and these sequence detectors, sequence generators, they actually generate your control signal. But I think this is sufficient for this particular course. So, but I would like to give you some assignments. We had previously some 7 to 8 questions. I don't exactly remember the number, but I will give some additional questions as an assignment. First, say design a counter that counts first 8 even numbers. Fine. Okay. Then another one, design a counter that counts first 8 odd numbers. Fine. And additionally, the circuit should output a binary 1 if the count is prime. Okay. If the count is prime, like 3 is prime, 5 is prime, 7 is prime. So every time you have odd but which is prime, it should display a 1. Okay, we'll stop here.